Now we get into a little bit of, not the crazy stuff, but a little bit more technical stuff, guys. We've dealt with most of the models already, most of the calculations. Let's have a quick look. Learning outcome statement 6H. Explain the instability of the coefficients. Why would your coefficients perhaps be not as stable as we would like? Okay. Financial data is dynamic and keeps changing, causing time series to be inherently unstable or non-stationarity. And remember, the minute something's non-stationary, it's not the best news for me, is it? Because in order for me to use AR models, autoregressive models, I want the data to be covariance stationary. I want it to be stable, but generally speaking, it may not be. Okay. Good. The shorter the time period, the greater the stability. Am I right? As with anything, not too many changes over a short time period. Okay. But remember again, guys, the shorter the time period, the less reliable the data, because the more data, the more reliable the model. So I'm caught between two little, both sides over here. When looking at time series models, guys, we need to assess if there's been current changes to the process. Okay. For example, exactly what we spoke about a little bit earlier. Ask yourself the question, have there been anything like a regime change of sort, a structural change, a change, for example, over here we look at a change in the tax rate. Good. Remember, as soon as there's been something like that, what do we say? The model becomes unreliable. Okay. Good. Based on this, we can conclude that in addition to examining for autocorrelation, what else? I can test for autocorrelation, and what I keep doing, guys, if remember, autocorrelation is not good for a AR model, and if I detect autocorrelation, then I move from an AR1 model to an AR2 model, etc., etc. But what's the other test I've got to test for as well? I want my data to be, okay, I want no autocorrelation, and I want no, and I do want covariance stationary. You guys comfortable with that? So those are the two things. If I had a perfect world, what would I ask for? I would ask for no serial correlation and covariance stationarity. You happy with that? Okay. In order for the assumption of covariance stationarity to be in place, we've seen those three already. Okay, let's move on. Okay. We come to a new term over here, a random walk. Okay. What's a random walk? When the predicted value of the model, okay, in one period will equal the value from the previous period, plus a bit of a random term as well, a random error term. That's your normal picture that we see, isn't it? Okay, nothing different over there. That's called a random walk. Look over here. Okay. Generally speaking, the equation will be expressed as follows. Okay. By the way, what does the error term have? Am I boring you yet? Okay. We saw all of these. Remember, where did we see these, guys? These are my normal principles from regression analysis. The expected value of the error term is 0. You've seen these as part of your 6 rules. The variance of the error term is the same for all observations. What's that called, guys? Hetero or homo? Homo, good. And the residuals are independently distributed. We've seen that, all of those before, so nothing new over here. Okay, that's a random walk. Okay, so a random walk looks a bit like that on the top of page 15. A random walk with a drift, fancy term. Okay, with the intercept term, okay, because what did I drop with a normal random walk? Look over here, guys. This is my normal random walk on the top. What's not there? The intercept. So a random walk with a drift is when, and why did I leave the intercept out? Because it was 0. What if it's not 0? Then it's got a bit of, that's called a random walk with a drift. Okay, so then I've got to put that back in. Does this not look, okay, very similar to our normal AR models? Okay, BO, XT is equal to BO plus what? B1 last period plus your error 2. Nothing different over here. You happy with that? This is just called a random walk with a drift. A random walk just contains no BO because we assume the random walk to be 0. Okay, good. Okay, let's go. Must be kept in mind that both the random walk, and we talk about the random walk's got no B0, you happy with that? And the random walk with the drift do not exhibit covariant stationarity. Okay. What do I want? Covariant stationarity. Both of these, okay, so the random walk plus a random walk with a drift do not exhibit covariant stationarity, which of course is a problem for me. Okay. What am I assuming in a random walk with a drift, guys? I'm assuming that the B1 is equal to 1. And let's see why we say it's equal to 1. Just keep that in mind for now. But remember, let's try and keep it as simple as we can and we don't overcomplicate things. Random walk, no, the B0 is not there. Random walk with a drift, there is a B0 now because it's not 0. Happy with that? Okay. But what am I assuming at my B1, my intercept, sorry, my slope is equal to 1. Yep. Correct. Why and why did I leave it? If you really wanted to, Werner, you could go and express your random walk with a B0 as well in it, in the equation. But what B0 is? 0. Random walk with a drift assumes that B0 is not 0. That's the only difference. Fancy. Both of them are assuming what? That it is not covariant stationary. Which is what? A problem. I don't like that. Okay. And very important, we'll just take it as gospel for now. We'll get back to it in a second. Okay. I'm assuming that B1, remember the equation for a random walk and with a drift, I'm assuming that B1 is equal to 1. That's what gives us its very definition of the random walk. We'll see why. Okay, but at this point, just take it as gospel that B1 in a random walk is equal to 1. Could be both. Remember, the random walk with no drift, just a simple random walk, only differs in the B0, doesn't it? Only in the B0 is the difference between a random walk and a random walk with a drift. Correct. So they're exactly the same in the B1 term, but it's the B0 term that differs for a drift and no drift, or no drift and yes drift. So if we just to stop here for 1 second, guys, let's just make ourselves a bit of a picture. Okay, what a horrible looking line. We didn't teach the machine to learn that well, did we? Strange lines. Let's go over here. And let's go here. Now, if I have to say, let's put over here. Here I'm going to put random walk. You happy? And here I'm going to put random walk plus a drift. Happy. Random walk. Okay. My B0 is equal to 0. Equals 0. And random walk with a drift, it does not equal to 0. You happy with that? Okay. My B1 is equal to 1 is equal to 1. It's as simple as that, guys. Okay, sometimes it's easier to see in a bit of a graph, a table form. Okay, you guys comfortable with that? Okay. And with both, and let me add in another one. Covariant stationary, no, and no. You happy with that? And if it's not covariant stationary, I'm unhappy because it starts to compromise. Remember, what we want 2 things to use time series or AR models. What are the 2 things that I want? I want covariant stationarity and I want no auto or serial correlation. Okay. Anyone comfortable thus far? And guys, it seems quite crazy, but let's keep it as simple as we can. Guys, remember my equation for mean reversion. There he is again. Mean reversion is equal to BO, okay, and 1. You happy with that? So remember, there's my mean reversion equation. Now, in a random walk, both a random walk and a random walk with a drift, B1 is equal to 1. What if I put, so we know B1 is equal to 1. What if I put it into the equation? What's 1 minus 1? 0. Okay, and any numerator, not dividend, apologies for that, divided by 0 is undefined. What do we call this? Therefore, whenever we've got this thing, B1 equals to 1, we call it, this is the fancy word, guys, you're going to see it many times, a unit root. Something I don't like. I don't want a unit root. A unit root is not what I want. If I take you back down here, and even make this a little bit, expand our table just a drop, and the unit root, yes, yes. Happy with that? That makes sense. That's the end of your table. Okay. Everyone comfortable? Now, you know. Now I can't use an ARL model. Simple. Okay, after all of that, then after all of that, that was the conclusion. You can't use an ARL model. Okay, well done. Look over here. And we conclude that here. Based on this, time series data that is not covariant stationary. Now, if it's not covariant stationary, then it probably exhibits a random walk with a drift. Then it's got a unit root of, well, it's got a unit root, and I can't use it. The estimated regression for AR1 will not work unless I do what? I transform my data. And sometimes, guys, you're going to hear the concept of the data before we can use it needs to be transformed. This is one of those cases. Let's have a look further. Okay, but guys, if you keep this table in mind, you're going to be you're good to go. Okay, good. Let's go. Top of page 16. Based on what we said in the previous learning outcome, the random walk plus a random walk with a drift do not exhibit covariant stationarity. Okay, we now look at how to test if it's covariant stationary or not. So now we've got to test, is it covariant stationary? Remember, that's the key test. If it is covariant stationary, tick yes, I can use auto AR models. If not, okay, then what? Another fancy word, if it doesn't exhibit covariant stationary, that it's probably got a what? A unit root, very fancy word for a whole lot of nothing. Don't let it upset anybody tonight. And there we go. Let's go. Number one, what could I do? I could perform an AR model. So run your model, like we did already, remember that? And then do what? Test for autocorrelations. You happy with that? Okay. Okay. And just look at this. Tell me if you like this. Okay. We've done this before already, by the way. We tested it when we looked at an AR1 model versus a AR2 model. We tested it for this already. If stationarity is, so step one, guys, run a model. Step two, test that model, that AR model for autocorrelation. Okay. If stationarity is present, okay, then what would we say? All of my lags that I'm testing are statistically indistinguishable from zero. Okay. Or if they are, guys, if let's say, for example, they are a problem, in other words, there is autocorrelation, then I move to what? Or the autocorrelations will move to zero as I do what, guys? Just increase the number of lags. Go AR2, AR3, AR4. You happy with that? So if AR1 doesn't, so step number one, guys, what I do? Test for, so run a model. Happy. Test for autocorrelation. If it doesn't work, in other words, if I'm detecting serial, and remember, guys, I use absolute values. Just remember that one. Don't let that trick you. Okay, and if there is a problem, increase the lags. But you can see the fancy words. Oh, look at these nice words. Increase the lags, test for serial autocorrelation. You never thought you would be talking like this. Okay, it's not normal talk, is it? Please don't talk like this on a Sunday with your friends. You won't have any more friends. Okay? Talk like this only in class, and specifically not to your spouse. I think you'll scare them away. Next test, what you could also, guys, it's so important that you don't get bogged down in the XT minus. Look what we're doing here. I'm trying to test if there's autocorrelation. I'm trying to test, because remember, if there's a problem of serial correlation, then I've got also a problem of the terms are not covariant stationary. I've got a unit root, blah, 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 blah. B1 is equal to 1, etc., etc. Okay, how do I test for this? Test 1, we've dealt with. Test 2, the Dickey-Fuller test. Okay, this is a far more conclusive test than the one before. Okay, is Dickey and Fuller convert your model, your AR1 model, and they run a simple regression. So step number 1. Okay, please don't worry too much about this. Just get the understanding over here, guys. You start with your basic model. We know the basic model by now, your basic arrow model. Step 2, you start to do a bit of a conversion on them, and you've converted or transformed the data somewhat. Okay, and now you just test for this. Okay. Okay. That's all we're doing over here. And I've written it over here. Please don't spend a batch of time on this. Just get a general understanding of this. Okay. What do we do? We do this by performing a modified t-test. And what am I looking at? Because remember, where's my problem going to be? My problem is going to be if B1 is equal to 1. That's a unit root, isn't it? Because if B1 is equal to 1, then my mean reversion is, I'm dividing by 0. Am I right? Because what's on the bottom? B1 minus 1, am I right? Who cares what's on the top? Well, it's B0, but what's on the bottom? B1 minus 1. Now, if B1 is equal to 1, I've got a problem, am I right? That's what I'm testing for. If that is equal to 1, then I've got a unit root, then my data is not covariant stationary. I found we're repeating a lot, but okay, there we go. Okay, and please don't spend a lot of time over here. I've given you a bit more detail on Dickey-Fuller. Don't spend time there. Okay. Okay. Top of page 17. In the event, guys, that I run the Dickey-Fuller test, and they're not going to ask you to run one, by the way. Don't stress about that. They're going to give you some numbers over there. And tell me what this means. So I run the Dickey-Fuller test, and oh my gosh, it's a random walk. What does that mean? Straight away, what did I say? Random walk, B1 is equal to 1. I've now got a unit root. My data is covariant stationary. No. Thank you. No, it's not covariant stationary. I'm just trying to see if everyone's still awake after 8 o'clock. And it's not covariant stationary. You happy how all those terms work together? Random walk equals B1 is equal to 1 equals unit root equals no covariant stationary, and I've got a problem, don't I? Now I can't use my AR models. What I need to do? I transform the data to make it what? Covariant stationary. What I use? Very fancy term called first differencing. Okay. I don't want you to spend a lot of time on this. All I want you to know about first differencing, guys, is that first differencing works on a process to do what? Transform the data from being covariance, not covariant stationary, to being covariance stationary. Okay, I'll just restate some of my numbers, and lo and behold, when I run the equation again, I've got my B1 to equal 0. Don't worry how I got to do that, guys. And of course, then the whole thing does work. Happy with that? Okay. Again, all I want you guys to know is this is called first differencing. And what does first differencing do? Why do I need to do it? I need to do it because I've got a random walk. And because I've got a random walk, I've got a problem. Okay. Let's look at some data over here. Again. Let's look at this as an example, but please, this is not an area I want you to spend too much time. I want the understanding here more than anything. We're looking at to predict revenue numbers for a large retail company. The following data has been presented for the last 8 quarters. Okay, good. Here's some numbers for you. The first differences are represented by YT over there and YT minus 1. So once I first difference the numbers, a fancy word, okay, then I start to get, my data then becomes covariant stationary again. Okay, regression output for the first numbers will be produced, and we can use this model provided that the estimated coefficient is less than 1, because if it was equal to 1, if B1 is equal to 1, I'm back where I started again. Okay. Good. And assuming that once I don't spend time on that example, I've just given you probably too long an example to show you what we really just wanted to show you. Assuming that the estimated coefficient is less than 1, in other words, that B1 is less than 1, I can use AR again, can't I? I'm back to my normal AR model again, because the minute B1 is less than 1, it's not a random walk, it's not a unit root, it is covariant stationary, and a happy am I. Of course, it'll be. As long as it's not 1. Now remember, it can't be less. It can't be equal to 1. That's your key issue. Because remember, look at my number. Okay. So it's B0 and 1 minus B1. So if you happy with that?
So you're just removing the lab as opposed to evidence.
It's a simple process. You don't have to know how to do it. Okay, I've never seen them ask you to first difference in a question before, but I need you to understand what they're trying to achieve with first difference. Because remember, once you have first difference, you have first differenced, then what can you do? The data now becomes, you've transformed. What does first differencing do to your data? It transforms the data from being not I don't know, that must be a fancy word, not covariant stationary into covariant stationary. Now once it's covariant stationary, everything can work again. Back to AR1 models again. You happy with that? That's the okay. Obviously, guys, if you were doing quant level 5, whatever it is, we could go detail into how to first difference, etc., etc. But then, of course, I would bring Mo in here to teach that to you. Okay, I wouldn't risk that myself. Okay, but guys, on a very simple level, okay, you guys happy where we are? Okay. And guys, by the time we finished time series, okay, you should be able to really summarize time series in your head in literally about 5 quick minutes. It's not, there hasn't been that much brand new stuff that we've seen tonight. It's very much a derivation of simple and multiple regression. Okay, we look here at seasonality, guys. Seasonality is a time series. In a time series is a pattern that repeats itself year on year. Black Friday sales in November, same pattern. Am I right? Nothing's changed. Okay. An example of seasonality, we've seen certain strong sales growth in certain months. For example, in December, the Christmas period, maybe there'll be followed by a very weak January sales. Okay, unless of course you're in perhaps tourism. Okay. Good. Okay. If there is seasonality, guys, look how your sometimes your data will change just a little bit. Because remember, XT, let's say for example now, guys, I want XT to be my December results, my December sales. What's the best thing if I'm using time series to compare to, if I'm using monthly data? Not XT minus 1, because then I'm comparing XT, which is December, to XT minus 1, which is November. What do I want to compare December to? Last December. Now you see why I use XT minus 12. Because in seasonality, that's the better comparison, isn't it? Does that make sense? Okay.
From a practical point of view, do they ever use anything other than that? Because, put it this way, when you're trying to budget or predict what sales are going to be like this year, and you go back to last year, the exact same month, might always be some sort of growth. Might be later or in reaction.
Yeah. So
it might not be 12 months, it might not be 13 or 15 months.
correct. So as long as you have understood the lag in the seasonality, you'll be fine. But again, you'd have to do that work. You have to say, well, generally speaking, my sense is that in terms of particularly about retail seasonality, it's quite predictable. It's just you can really see a little bit. Yeah, yeah. Mm. Yeah, no, you could definitely get some. And I was looking at a. Hopefully we're going to finally move a little bit ahead on this modeling course that I've been promising everybody. And when they look at the models, the proper modelers, okay, and they're looking to model now, let's say, for example, their working capital, okay, they don't just model based on 365 days. They take the year, then they run an Excel number over there. They use date minus date, so you get exactly the 2019 less 2018. Perhaps there might have been 366 days in that year. So that's much more accurate. Work days, yeah. Again, you can your model will only be as accurate as, remember, it's rubbish in, rubbish out. So the better stuff that you put into it, the better it will be. Happy with that. So this kind of stuff, you really have to go and do a bit of digging. Like, remember, what if November, black whatever, I don't know what it's called anymore. Okay, the sale, call it the sale. Okay, last year happened on the 24th, perhaps. Now it's the 29th. Does that have an impact? Yeah, because remember, most salaries are paid on the 24th, 25th. So if Black December, November was before that cut-off date, that would have impacted someone's salary, wouldn't it? The sales commission guy. Now it doesn't. Now it goes. I have no idea when it is. White December, Black December. I don't know what they're even talking about. Cyber this, Cyber that. And then I saw Apple came out to sales now. Grey November. My word. Grey Friday. I don't know what. I don't know. Head spinning. My phone has literally been beeping the whole day. I've been offered sales from Woolworths. I have no idea. Okay. And I just said, I feel so completely blessed, to be honest with you, going into Black Friday, that I don't need anything. You know what I'm saying? I just think, like, my wife shouting me, she said, please, can I get you something that you need? I said, I've got jeans and a t-shirt, and I've got a wonderful class. Happy am I. Am I right? What else do I need? Okay. I like what I do. I like my job. Okay. Yeah. I mean, I told you guys, I shopped with my kids yesterday. My older boys they're all going on camp. So they all needed tackies. 95% into the shop, when they'd all found their nice tackies and everything, then one of them turned to me in a moment, I think perhaps of weakness, and said, don't you want something also, Dad? And I said, sure, I'm not trying to sound like a saint or anything, I could buy more. It's always nice to have a third or fifth pair of tackies, but do we need it? You know what I'm saying? Like, when I look at it, anything that I'm like, I've got to wait until November, the 20-something of Black something, December, to get that specific thing. Okay. And most of us don't, by the way. It's nice to get new stuff, of course, but okay. Good. Tell me what you think over here. Let's go back. Graham, this is on you now. It is a seasonal model. You happy with that? And I ran this equation. That's my regression. That's my AR1 equation. What do you guys think? Good or bad? It's bad. Why? Because it shouldn't be xt minus 1. It should be xt minus 12. Probably the model is going to be incorrectly specified. You happy with that? But no problem. What do I do? Okay, I run myself, and this is the way to test it always, guys, isn't it? What do? You run yourself an AR1 model, you run your autocorrelations, you run your lags. And how many lags would you run? Well, here it's a 4-quarter, so you run 4 lags. Go to the 4th quarter. You give your 5% level of significance, okay, and look over here at a 1.99. What are you picking up, by the way? Okay, I've got a problem, don't I? Because look over here, if I got a critical value of 1.99, absolute, what have I got? Where am I winning? Where's my issue? Fourth quarter, Mike, can you see that? Okay, I'll read it to you. Only the fourth autocorrelation is seasonal, and we reject the null that is equal to 0. Why? Because the t-stat at 6.5 is much, much greater than 1.99. Okay, all the other t-stats were fine, am I right? So these are probably not seasonal, am I right? And that's how you can pick up your data. You guys comfortable with that? Nice and easy. Okay. Okay, now I picked up, and guys, can you see how you pick up perhaps seasonal issues? I picked up seasonality. What am I going to do about it? Okay. A nice, quick and easy approach would be to insert a seasonal lag. So if it's in the fourth quarter, what I do, we'll add in a fourth quarter. You happy with that? This is almost like what? AR2 now. AR1 didn't work. Now I'm going to go to a, and not just an AR2, but a seasonal lag. No, they're not relevant to me. Because my current period sales is not determined by them at all. Okay. Could well be. Okay, top of page 19, guys. And I'm not going to do this whole question with you because I would bore you to tears. We've seen this about 100 times. Just to explain the question to you. Okay. And look what I've done over here, just in terms of my numbers. I've added in now a what? A seasonal lag T minus 4. You happy with that? Because when I ran my first model, my AR1 model, it didn't work. I thought, oh, let me check. Perhaps there's a seasonal lag there. I picked up the big difference between my critical value and the t-stat. I run my numbers again over here. Okay. And let's see what I get. Okay. And now my critical value is 1.99. Let's go for absolutes. And what do we say? No issues over here because they're all less than 1.99. So there's no serial correlation. I've removed the issue of seasonality. And now I can go and do my predictions. You happy with that? Does that make sense? Always the same. Because it's all in the same data. It's all in the same data, just for different periods. But they should be the same, shouldn't they? At least a link between the two. Okay. But remember, don't make the same mistake over there on the top. There, the standard errors, of course, are going to be different because they're completely different variables. That is BO, that's B1, and that's B2. Those are completely different variables. These are all the same. I'm just looking at the lags in the data, but the standard errors are always going to be the same. Okay, there we go, guys. Okay. Just very briefly, I don't want to waste your time on this because I know you know how to do this, guys. What if I wanted to work out what my current period sales are going to be? What do I do? BO I've got, haven't I? BO, where? Just show me over here, guys. Where would I get BO from? What is BO? Happy with that one? That's my BO. My B1 and B2 I've got. Okay. And I also know what the numbers were, don't I? Sales growth last quarter, 1%, plug that one in. And sales growth 4 quarters ago, 2%, plug that in. Over there. You happy with that, guys? It's a plug and play. Nothing that we haven't seen in terms of any of the normal regression thus far. Okay. Everyone comfortable? And over the page, there's just your numbers over there. If we just say to you, if you had to say, what are all those numbers? Let's go quick. Okay, that is B0, that is B1, that is B2. There's your 1%, that's the growth from T minus 1, that's T minus 1, and that is T minus 4. You comfortable with that? really just a case of a bit of plug and play. Okay, let's end off the last bit over here, guys. Okay, we've dealt with autoregressive models. Now I'm just throwing in one little bit extra. Okay. In the event that the variance of the residuals in the current period is dependent on the variance of the residuals from the previous period, what do we say? We call it an arch model, an autoregressive conditional, and it's not homoskedastic, is it? It is hetero. Hetero is bad. Okay. Heteroskedasticity. Okay. In such a case, the standard errors, okay, that are generated by an arch model would be invalid. How do we test for arch or gotch, guys? Okay. By the way, when we work with gotch, the G stands for generalized, but don't spend a lot of time on that. Okay. How do you test for arch, guys? Because arch is a problem, isn't it? Okay. We use an arch model when testing whether a time series exhibits arch. What's arch? Autoregressive conditional heteroskedasticity. And as Werner says, that's bad. Okay. It sounds bad, doesn't it? Okay. Tell anybody that they're suffering from autoregressive conditional heteroskedasticity, he'll panic, won't he? Okay. Go tell the doctor to tell a patient that. Okay. He'll leave straight away. Okay. And now you know it's not a good thing, this arch. Okay. We use an arch model. Okay. When testing whether time series exhibits arch, we need to regress the residuals from the estimated time series against, you go at the first lag, t minus 1. Okay. You're not going to spend time on these, guys. Okay. In the event that the coefficient is statistically different from 0, okay, we say arch is present. Okay. By the way, what happens if arch is there? Oh no. Okay. It's bad. Okay. We need to correct this by using a generalized least squares regression technique, and no, don't spend time on that. Just know what you have to do. Very similar to what we saw with the unit root I used. First, differencing to get rid of my unit root or my random walk. Okay. Predicting the variance of a time series is another formula for you. Don't spend time there, please. Okay. Let's look at a little bit of an example. Okay. Source of the data, let's give some credit, is from the CFA Level 2 notes. Okay. Assume that we know that arch exists. We can predict the variance of the errors. So arch does exist. And then you'd say, oh no, that's a problem. We don't like arch, autoregressive conditional heteroskedasticity. And that tells me that there's issues. I can't use an AR model anymore. I've got to just fix that up first. La, 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 la. How do we calculate the variance of the errors? Well, there's the numbers, guys. Okay. There's your intercept, BO. There's your t minus 1. We've seen all of this before. Okay. And there's just some, there's your equation. So you put your intercept over there, your B1 B0 there, your B1 over there. I'm assuming that the error is 1%, and because it's variance gets, I square it. Happy with that. Just in case they ask it as a question. I haven't seen them ask it that often as a question, but yes, they could say to you, oh, by the way, arch is present. How do we calculate for arch? And then you would run those numbers.
So, for it,
What?
You leave out
But correct. But they give them to you. Yeah, they give you the coefficients. They give you 9.1, 0.21. There's your two coefficients. Okay, there's B0 and there's that one. All it is that they've also got to give you then the predicted error, the error in the period, and because it's variance, you square it. That's all. Nothing fancier than that. Okay. Last little bit, guys. Okay, I should make you read this on your own because this is where it gets a little bit, not complicated, but okay. We can avoid the complication. We never do that. Let's go. We've been working with time series data that only contains one time series. Up until now, it's been fun, hasn't it? Almost a little bit like what? Simple regression. Not too crazily different. Okay. We stated that in the event that the time series contained a unit root, then what? Unit root equals B1 of 1 equals random walk equals not covariance stationary. And how did we fix this, guys? We used the Dickey-Fuller test to test, and then we had to transform the data with first differencing. Good. We now have a quick look, guys, and they don't focus much on this. What if I now have not one time series data, but two data that contains two time series? Okay. One of the time series corresponds to the dependent variable, and one corresponds to the independent variable. You happy with that? And you go back to remember this equation, that your y is equal to b0 plus b1 times x. Let's give an example. The analyst is trying to attempt to predict the stock market performance, okay, by looking at the P/E ratio of the market index. Everyone comfortable? The stock market performance is y. Why? We're saying that is the stock market performance is dependent on the P/E ratio. You happy with that? Okay. Now look over here. If I'm using two time series, not one but two time series, okay, both the X and the Y are time series data. Do you agree with that? Y, stock market performance, is based on time, and the P ratio is also a time-based time series data. It moves with time, doesn't it? Okay. Now what do you have to do? It's actually not so crazy at all. You need to test for unit roots in both the X and the Y. Okay. Now let's have a look. Neither of the time series, the X nor the Y, has got a unit root. What would you say? Brilliant. Okay. The independent variable has got one. Okay. Or the dependent variable has got one, or both of them have got one. Okay. Problem, and problem. I can't use linear regression. You happy with that? But now just remember that number 4 and 5 is just the last little bit. It's not even overly complicated, but it just introduces a new word. In other words, both variables have got unit roots. Now we've got to ask the question, are they co-integrated, the two series? Fancy word. Because if they are co-integrated, even though that they both got unit roots, which is normally a massive problem, I can still use them. But if both of them have got unit roots, but the data is not co-integrated with each other, they don't work together, then of course I can't use them. But no one shouted at me and said, what's co-integration? Okay, it's on the next page. You should have all shouted. Okay, yeah. You can scream in the class, I don't mind. Not too much, but okay. Co-integration, when the two time series that we're working with are economically linked. Okay, it's almost as if they almost and now they both got unit roots. It almost works against each other. Okay. In the event that the variables contain unit roots but are co-integrated, this was case number 5 from the previous page, the regression can be used and will be reliable. Okay. And I'm not going to give you anything more than how to test for co-integration. Okay. You use the Dickey-Fuller test and the critical values, and please don't spend time on this, obviously. Not even an example for you. You use the Engel and Granger, I don't know how you pronounce it, tables to get your critical values. Not a thing we're going to be spending time. You happy with that, guys? So remember, all that I've done over here, when I've now introduced more variables, as I've said to you guys, there's more variables now, guys. What am I going to do? Okay, well, this is the summary, guys. This is it. Let's go. I just want to do this one more time just to make sure we've got it. Okay. Neither has got a unit root. Brilliant. I can use it. Independent's got a unit root, and the dependent not, can't use it. Dependent's got a unit root, the no, can't use it. Now the question 4 and 5 is, what if both have got unit roots? Now I've got to ask myself the question, is the data co-integrated? If it is co-integrated, okay, then in other words, economically linked, I can use it. If not, I can't use it. How do I test for co-integration of the data? The Dickey-Fuller test again. Nothing more fancy than that. That's it. That's all I want you to know. Okay. Let's move down. Okay. And guys, I'm not spending much time on this. Okay. This is just really, guys, a summary of what we've seen in the whole picture thus far. Steps in time series forecasting. Okay. Okay, let's have a look over here. I'm going to go through this quite quickly. The following steps are suggested when building a time series model for prediction. Number 1, understand the investment problem and decide on the model of choice. Now, when we talk about the model of choice, we know, is it a linear model? Is it a log linear model? Is it an AR model? Okay. Number 2, if a time series model is selected, what must you make sure, guys, am I boring you yet, that the data is? How do you know if it's covariant, stationary? Okay, what are the 3 things that what must not move? The mean, the variance, and the covariance. Good. Okay, now, good. Number 3, in the event of that no seasonal or structural shifts, then I can use a linear or a trend model. We know how to do all of those, guys. I'm not spending time over there. 4, if autocorrelation is found, maybe go and use an autoregressive model. Okay, if the model does have autocorrelation, okay, I cannot move ahead unless I check for stationarity. If it's there, I may need to use first differencing. We've seen all of this before, guys. All of this is just really a summary of what we've seen thus far. 6, now that our data has been transformed, we can use an AR model. Okay. What if you detect autoregression in AR1 model, then you go and use a AR2 model. Check for seasonality, 0.8. Okay. 0.9. Okay. Check for arch. We saw that also, guys. And 10, test the models out of sample compared to in sample. Because remember, you want your out of sample to be as, if not, well, as good as your in sample. In sample is fine, but it's also got to work when it's out of sample as well. Guys, don't spend a lot of time on this. It might help you just to, if you've understood this last page over here, guys, you've got the whole chapter in your hands. Okay. But guys, it is a little bit, I don't know what you want to call it, not overly difficult, but it's tricky. You've got to really keep your head about you. Okay. And now that Chetan's not here, because now I know where he normally sits at the back over there. And he's normally one that votes against a question before we leave, but he's not even here, so there's not even a vote. Isn't that nice? But we'll just do one. Okay. You've all lost your vote. Okay. Okay, and let's go. I want to go and look one of the first bit is all just like individual questions, guys. I want to do a longer one. I said only one question, but it didn't say how long it will be. Okay, let's go and have a look. There was one I had in mind. Here we go. And guys, when you start to look at this, it starts to look a little bit crazy, doesn't it? Now it looks important and impressive. Let's go. Guys, has anyone not got? Grab. Guys, all got. Perfect. Everyone got? Okay. And guys, I'm doing the following information relates to question 20 to 26, which is page 445. Okay. And let's go. Angela Martinez, an energy sector analyst at an investment bank, is concerned about the future level of oil prices and how it might affect portfolio values. She's considering whether to recommend a hedge for the bank, okay, to hedge the bank's portfolio exposure to changes in oil prices. Martinez examines WTI, which stands for West Texas Intermediate, monthly crude oil price data expressed in US dollars per barrel for the 181 month period from August. So straight away, guys, you can see, let's just start to label stuff. Her period is 181 periods from August 2000 to August 2015. The end of month WTI price, okay, was $51.16 in July. So let's just go over here, guys. There's July 15. You happy with that? And the price was $51.16. And for August 15, the price was $42.86. You guys comfortable? Okay. After reviewing the time series data, Martinez determines that the mean and variance is not constant over time. So what would you say? The data is not covariance stationary. She then runs the following 4 regressions with the time series data. Linear trend model, you know. A log linear trend model, you know. AR1 model and AR2 models. Exhibit 1 presents selected data from all 4 regressions. Exhibit 2 presents selected autocorrelation data from the AR1 models. Okay, there's all your data. Okay, over the page, there's your, in Exhibit 1, guys, the 5% level, the lower critical value for Durbin-Watson is 1.75 for both linear and log linear regressions. There's some more data. There's your autocorrelations. Okay. And if you have a look over there, guys, look what it tells you. Okay. In the note. See a little note over there? Very important. What does it say? At a 5% level of significance, the critical value for the t-stat is 1.97. You happy with that, guys? Okay. In other words, what? They're not giving you a t-table. They're not asking you to go and find any values. Okay. If we move down, after reviewing the data and regression results, Martinez draws the following conclusions. Conclusion 1. The time series for WTI oil prices is covariant stationary. No, they said it wasn't. Because they said that what? That the mean and the variance are not constant over time. Therefore, it is not covariance. Okay, and you just pray that they give you that one because it's a free mark for guys like you. Am I right? Okay, number 2. Out of sampling forecasting using AR1 is more accurate than that of the AR2 model. Okay, we can have a look at some of the data over there, guys, but generally what would you say? Is that right or wrong? Okay, you said it sounds a bit funky, but we're not going to use that as a complete thing. We'll keep that in mind. Okay, guys, let us jump straight in over here, guys. And it says, based on exhibit number 1, the predicted oil price. Okay, in fact, guys, I'm tired. It's getting late. Okay, so I want you to do 20 and 21 yourselves. You've got 4 minutes. Get busy. Because the funny thing is, guys, I'm not really tired. Okay, but I can do these. After teaching this section for a long time, I can do these, and I want to make sure. It's always better if you do them first yourselves. Don't look at the solutions, of course. Look at 20 and 21. Get to work, guys. I'm giving you 4 minutes. Let's go. Everyone comfortable? Nice and easy stuff. Nothing too crazy with those. Let's just have a quick look, guys. Number 20, based on exhibit 1. Okay, and it said to you, please use the linear trend model. Okay, what was if we have a quick look over there, if I'm going to just take you back there, on the linear trend model, what would you be using? Okay, there's your linear trend model. You guys comfortable? There's your B0, happy? There is your B1. Okay, And then it said to me, they wanted me to predict for what period, guys? October's what in the numbers, guys? I did how many observations? Let's go have a quick look. I used 181 from August to August, am I right? So the 181 was from August 2000 to August 2015. What do I want? So August is 181, you happy? September is 182 and 183. You guys comfortable with that? If I just show you the equation over here, I'm not going to do the maths with you. That's just a bit of extra stuff they put in, not nothing that we need. No, don't stress at all about those, all the other little minuses under the coefficients. Don't worry about those. Okay, it's something extra they put in, nothing that we use at all. Okay. Okay. You guys comfortable? Okay. Try to make it a little bit bigger over there. Can you guys see a number? If I just take you to the solution over there, you comfortable with that? The only little trick over there was make sure that you use the correct t. That t is equal to 183. You guys comfortable? But there's your B0. There's your B1. There's nothing else to add any value. When I move to 21, guys, okay, and then here they spoke about what? They wanted it for September. So now what's my T, guys, by the way? 182, good. And remember what I do, I run all my numbers. Okay. You happy with the coefficients, guys? 3.329, 0.07, is it 5 or 3 times 182. You happy with that? What do I get to, by the way? I get to an answer of, this is a little bit of a trick, 4.7579. You happy with that? And that's just from looking at running the regression and just putting the numbers into the regression. But then what I have to do with that 4.7579, I've got to go second function, ln, and then I get to my real answer of 11650. Okay, that's obviously, guys, the minute you start to use a linear model, a log linear model, then I need to use those. You guys comfortable with that? Nothing too crazy, but okay, good. Okay, let's go and look at number 22. Is everybody with me? Okay, 22. 22 says, based on the regression output in Exhibit 1, there is evidence of positive serial correlation in the errors. In what? So let's go back to Exhibit number 1. Okay. And let's have a look at my, just before we carry on, guys, look on the top of the neck of page 446, and what did I say? It says, in Exhibit 1, at the 5% level of significance, the lower value on the Durbin-Watson is 1.75. You happy with that? Let's go back. Okay. Now, which ones am I looking at over here? Okay. And they're talking about linear and log linear, by the way. If you just see from this, from the solutions, and what are they saying? Okay. Look at my, so remember my Durbin-Watson, and it's got a lower level of 1.75. The high level, I don't know. They didn't give it to me, but it's higher than 1.75, isn't it? Make it whatever you like. Where do the two Durbin-Watsons for linear and log linear sit? 0.10 and? So for linear, there's log linear and there's linear. And where do they sit? Log linear is well below the 1.75 lower level. You happy with that? And linear is also well below the level as well. You happy with that? So remember, as it starts to get close to 0, what do we say, guys? Positive serial correlation, isn't it? And let me just prove it to you very quickly. I'm going to go, what's my Durbin-Watson? Durbin-Watson approximates what? To 1 minus r, you happy? Now if it's perfectly positively correlated, that will be a what? A 1. 1 minus 1, 0. 2 times 0, 0. So those are close to 0, aren't they? Both of those are close to 0. Okay, we're way off the 1.75, which would mean that what? That they are? Will you tell me, guys? 22. There's evidence of positive serial correlation where, guys? In both. You happy with that? You happy why I picked B? Okay. Your free mark, guys. Number 23. Who wants the free mark? Everyone wants a free mark. It's Black Friday. It's free. 100% off this one. Martinez's conclusion number 1 is correct or incorrect? But incorrect. Why? B or C? B is a bit easy because the mean and the variance are not constant over time. You guys happy with that? Please don't expect that in your exam. If you do, please also don't let out a squeal of delight because they will come and ask you what you are squealing about. Okay, good. Let's look at the next one. 24. Based on Exhibit 1, okay, the forecasted oil price in September, okay, based on the AR2 model, is closest to, okay, now let's go back and have, what is this AR2 model over here? Here he is. Okay. How did I do this one? Remember what I put over there in the right-hand column? I put the July and the August prices, didn't I? What is an AR2 model? Look at question 24. 24 wants me to work out the price when, guys? September. So September is equal to T. You happy? What's T minus 1 is then? Is August price, you happy? And T minus 2 is equal to July. And I've got those prices, don't I? So again, this is a plug and play. You happy with that? So if we run our numbers, let's run our numbers. I'm going to go all the way over there. We start off with the first coefficient. What's the first coefficient? 2.0017. You happy? Let's put it in. It's equal to 2.0017. You happy? There'll be a plus, and then there'll be another plus. Okay, first of all, what I know. In over here, my first price was what? 42.86, and over here my price was 51.16. Let's just change the color so we can see it nicely. You happy with that? And what I need to plug in next to these, I times them just by their coefficients, don't I? This is minus 0.4249. You comfortable? And this is 1.3946. Everyone see where I got everything from? Okay, and again, guys, it's really just a plug and play, isn't it? Nothing too crazy, and my answer is 40.03 once you run all the maths. You guys comfortable with that? Okay, let's go. 2 more. To get these last 2 right, we go home. Otherwise, we do the next one. Just kidding. Just kidding. Sure. Okay, let's go. Based on the data for the AR1 model number 25, guys, in exhibits 1 and 2, you can conclude that what? The residuals are not serially correlated, or that you can't conclude if you have a look at them. That the autocorrelations do not differ significantly from 0. You'll see over there that's also an issue. And now you pray for the last one. B, this is for you. Please do it for us. The standard errors, remember, of The autocorrelations, remember what did we say B? They stay the same, don't they? So let's run the numbers. Is equal to what? 1 over the root of t, am I right? What's t? 180, am I right? What do you get? 0.0745. A gentle one. Not too crazy a one, actually. So 25 will be C. That's how you calculate, obviously, guys, your standard error. Last one, you're on your own, guys. Based on the mean reverting level implied by the AR1 model from Exhibit 1, the forecasted oil price in September is likely to be less than $42, equal to $42, or greater than $42. Okay, now straight away, guys, what do? You jump into your formula. What's your formula? What's your mean reverting level? B0. Good, so it's B0, 1 minus B1. You happy with that? And we'll go pull up some data over there. B0 is equal to 1.5948. 1, what's B1? 0.9767. You happy where I got all my numbers from, guys? Okay, and what does it come out with? Well, what's the mean reverting price? $68.45. You happy with that? Completely just a plug and play, guys. But you can see how important the numbers that we've worked on tonight are. What do you conclude in number 26, guys? C, that is obviously greater than 42. You guys comfortable? Okay. But you guys have got a nice pack of numbers over there, guys. Got tons of questions, guys. Till we meet again, please. Okay. Spend a bit of time on questions on readings 4, 5, and 6. Next time we meet, we'll just knock off the balance of machine learning, big data, and algorithms. Guys, please don't forget to take a ticket on your way out. Hopefully the traffic has died down. Okay. It's one of the benefits, isn't it, of ending a bit later. No traffic. Okay. Everyone please drive safe, and we will see you next week.